600, 700 kV.
Late in 1960, the live line barehand method of line and station maintenance was announced to the electric utility industry. Because of the many economic benefits it offered, the new technique was received with immediate attention and interest. Since the barehand method was a revolutionary technique and one that required substantial revisions of long-standing maintenance procedures, utilities approached the subject with proper caution. But several years of field experience and extensive research and development work by the Live Line Department of Ohio Brass Company have brought about widespread acceptance of the new maintenance method. The reasons behind this acceptance are the subject of this filmed report. The original experiments with the barehand method were conducted in the Ohio Brass High Voltage Laboratory by engineers of American Electric Power System, Ohio Brass Company, and Holland Corporation, an OB subsidiary. By an application of the Faraday cage principle, these engineers proved that a man standing in a metal-lined bucket can bond it to an energized conductor without shock or discomfort if the bucket is insulated from ground. This bucket shielding is comfortable up to about 230 kV. At higher voltages, additional shielding can easily be attached to provide comfortable working conditions. Conductive sole shoes bond the men to their shielding, so both are always at the same potential. When the line is energized at 500 kV, the line-to-ground voltage of an 866 kV system, charging current sparks jump across the 32-inch gap between conductor and shielding. Attachment of bonding leads to the conductor brings men and shielding to conductor potential. A neon tube clearly demonstrates the effectiveness of the shielding. The tube lights up in the electrostatic field outside the shielding, but no field exists within the shielded work area. If a lineman puts his hand outside the shielded area, he would feel a harmless tingling sensation due to a very small charging current at his fingertips. This illustrates a basic difference between the barehand and the conventional hot stick method of live line work. With the hot stick method, any leakage currents which might pass over the insulated stick from the conductor to the pole must also pass through the body of the lineman. Barehand method, with the bonding lead attached to the conductor, a nominal charging current and the leakage current, if present, flow over the insulating section through the metal parts of the elbow and on through the truck body to ground. The barehand lineman is thus outside the arm current path. In performing live line work by the barehand method, it is essential to be able to determine, and under severe weather conditions to monitor, the amount of current flowing along the insulating arm. This arm current cannot be measured by placing a meter between the truck and ground, because a meter at this location would include not only the arm current, but also stray charging currents which shunt the arm and pass directly from the bucket shielding to the truck body and from the conductor itself to the truck body. The Holland aerial elbow provides a method for measuring the arm current, a method which eliminates from the measuring circuit the large stray capacitance which shunts the arm. Arm current is collected by a built-in electrode at the lower end of the fiberglass arm and carried by a coaxial cable to an outlet at the base of the lower arm. A meter, available from Holland, plugs into the outlet and measures the arm current in microamperes. Of the two components making up the arm current, The charging current represents a nominal 70 microamperes on the 55-foot Holland unit when performing work at its rated voltage of 138 kV. The second component, which makes up the arm current, is leakage, which passes over the arm because of contamination on its surface. Under severe conditions, this can produce an arm current reading of 200 microamperes or more. At the 200 microampere level, the arm is still safe, but should be cleaned. At readings above this level, the unit should be checked and serviced to restore the arm current to its original low level. In the Holland elbow, the inner surface of the fiberglass arm and all the control rods inside the arm are protected from contamination by a lifetime coating of silicone. Arm current measurements are an important part of the certification test received by every Holland live line elbow before delivery. A microammeter is plugged into the coaxial cable outlet on the lower arm to make the arm current readings. The meter used in the laboratory certification test is equivalent to that available for use with the elbow in the field. Frequently, other meters and equipment may also be used to verify the condition of the insulation. Using controls at the base of the elbow, the empty buckets are raised until the shielding makes contact with the conductor. This is the procedure recommended for all tests in the field. After the bucket shielding has made contact, the conductor is energized at the rated voltage of the elbow. Since this unit is rated for use on a 138 kV system, it will be tested at 80 kV RMS to ground, the line-to-ground voltage of a 138 kV transmission line. The arm current at this voltage, normally around 70 microamperes, is recorded for the purchaser. This certified measurement thus becomes a benchmark for subsequent field tests. After testing at its rated voltage, the elbow is subjected to a 1-minute withstand test to double its rated line-to-ground voltage, in this case at 160 kV, double the maximum voltage it will see in service. This voltage is held for 1 minute, as the arm current is carefully observed by lab engineers. This measurement is also recorded on the test certification sent to the purchaser. Because line work must sometimes be performed under adverse weather conditions, production line Holland elbows are frequently subjected to wet testing under high voltage. An engineer at the cab observes the arm current reading as the water spray is directed onto the arm. As the heavy spray strikes the fiberglass arm section, water droplets roll off quickly on both sides. This action of the water is caused by the silicone coating on the arm and by the slight crown built into the top surface. This prevents the formation of long water streamers down the arm, which could bridge out sections of the insulation. The effect on the arm current is clearly shown by the meter. The meter registers only small surges of leakage current, well within the normal working range of the elbow. As long as these surges do not exceed the 1 milliampere level, barehand work need not be interrupted by inclement weather. In this laboratory test, a 10-foot section of fiberglass arm and an 18-unit string of insulators, both rated at 345 kV, are connected in parallel to a high voltage source. Both will be subjected to increasing voltage until flashover occurs. At 700 kV, 800, 900. The insulator string flashed at 950,000 volts. A second shot. And both flash. These tests prove that the insulation in the Holland elbow is rated conservatively. Field tests on lines such as American Electric Power Systems research project at Apple Grove indicate that there is no practical upper limit for the application of the live line barehand method. This 65-foot hole and elbow is normally rated at 460 kV. On the Apple Grove 775 kV line, the arm current reading was 350 microamperes, well below the maximum permissible level for this equipment. The demonstration proves again the ample margin of safety built into Holon aerial equipment. Through experience gained in live line work throughout the country, job procedures have been evolved to take maximum advantage of the versatility, efficiency, and inherent safety of the barehand method. This crew is about to replace 3 broken suspension insulators on a 138 kV H-frame. Arriving at the job site, the truck is placed in a suitable position so the personnel buckets, when elevated, will be in a convenient location with respect to the work. The weatherproof covers are removed. These protect the personnel buckets and the fiberglass arm section when the elbow is traveling or in storage. The 4 stabilizing jacks are hydraulically powered and operate independently. They are paired, front and back, to form 2 powerful A-frames which lift the weight of the entire vehicle and provide a stable, level platform for work. If the ground is soft, timbers or cross-arm sections should be used under the jacks for firm support. Control levers at the buckets are duplicated by another set of levers on the pedestal. This set is used to raise the buckets for an arm current measurement. With the shielding of the empty buckets in contact with the conductor, the arm current can be read on the microammeter plugged into the coaxial cable outlet. If the meter reading is normal, work may proceed. If higher than the permissible level, the fiberglass arm section should be cleaned before use. This 65-foot elbow can lift 600 pounds from ground level, in addition to the rated bucket load of 500 pounds. At an angle of 75 degrees or more, the upper arm can lift 2,000 pounds, in addition to the bucket load. The linemen using this equipment climb no higher than the edge of the buckets. Safety belts allow freedom of movement in a safe, comfortable working position. Pole climbing accidents and pole fatigue are eliminated. The crew ascends to the cross arm, checking the structure carefully for hazards on the way up. A link stick is attached, and then the buckets are lowered to conductor height. After bonding leads are attached, the conductor is lifted slightly to slack off the insulator string. Doing the work is the small fiberglass boom mounted between the buckets. The boom has the same insulating quality as the arm itself and can be pivoted vertically and extended up to 6 feet in length. After the link stick is attached, the insulator string is disengaged and the conductor is lowered to the support of the link stick. Full feathering hydraulic controls have a firm, precise feel, allow smooth, gentle movements, pinpoint positioning. A variety of useful tools can be mounted on the universal head of the pivot boom. This tool, called a dishpan by the crew, comes in mighty handy when working with a string of insulators. Linemen who prefer to work with leather or cloth gloves can do so. The broken insulators are quickly removed and replaced. And the string held in the dishpan is reconnected. Demonstrating again the operator's precise control over the movements of the elbow. The hydraulic cylinders that actuate the hole and elbow are double acting, so the arm is raised and lowered under power with positive control all the way. If the hydraulic system, which has a 5-to-1 safety factor, should fail, check valves prevent any movement of the arms. In such a case, oil pressure can be released manually to lower the bucket safely to the ground. The hook is replaced in the pivot boom, and the boom is rotated and extended. Since the buckets are interconnected electrically, only one bond is required to bring both men to conductor potential. The second bond is thus a safety precaution. When the buckets are in close to the work area, the operator may push a slow-down control button to reduce all movements to a very slow crawl, even if the control levers are accidentally pushed wide open. This means greater safety, more accurate positioning, easier, more efficient, and faster work. On a job such as this, for example, a trained bare-hand crew will average less than half an hour from the time of leaving ground until return. With conventional hotline methods, the job would average about 1.5 hours, a ratio of 3 to 1 in favor of the bare-hand method. Another typical bare-hand job is illustrated by the work on this 33 kV corner pole. The line current will be carried by a temporary jumper as the crew replaces high-resistance bolted connectors with compression fittings. Their buckets are equipped with manually operated swiveling devices, which permit each bucket to be rotated horizontally up to 90 degrees or more in relation to the arm, allowing each man to place himself in the most convenient work position. Buckets remain level automatically in any elbow position. After the bolted connectors are removed and the wire ends cleaned, the jumper loop is cut to size, the men helping each other from their separate buckets. The deep tool trays, made of fiberglass like the personnel buckets, are a necessity for efficient work. The compression fitting is slipped over the wire ends, and crimped, first on one side, then the other. The work procedures shown in these scenes are familiar to every experienced lineman. The unique contribution of the bare-hand method is that it allows the lineman to do this familiar work close up, holding the tool in his hand instead of at the end of a hot stick. The longer the hot stick normally required for the job, the greater the advantage of doing it bare hand. Training programs conducted by the Ohio Brass Live Line Department have made competent bare-hand linemen out of experienced conventional linemen in 1 week or less of intensive training. Here's how a bare-hand crew changes out a broken ridge pin insulator on a 12.5 kV pole on a typical rural distribution line. A link stick is attached to the cross arm and an insulated barrier slipped under the near insulator. Barriers are used wherever necessary up to voltages around 69 kV, where clearances are no problem. The conductor is then removed from the insulator and lowered in the pivot boom to the support of the link stick. With the conductor out of the way, the men return to the top of the pole, move into the center phase, the bucket straddling the cross arm, and clip on to the conductor. Notice that both men always attach a bonding lead to the conductor before touching it. If either man should touch this 12.5 kV conductor before any bond was attached, he would feel a harmless but annoying charging current shock. After the tie wire is cut, the conductor is lifted into the pivot boom hook. Bonding leads are removed. The broken insulator is removed from the ridge pin, and the new insulator is threaded on the pin. Bucket swivels permit linemen to place themselves in the best working position. Bonding leads are again attached to the conductor, which is lifted from the pivot boom hook. Back to the insulator, and held there while the tie wire is applied. A busy intersection, on the ground and in the air, is the setting for another bare-hand job. The linemen and their highly maneuverable 55-foot hole and elbow have easily bypassed the heavy underbuild and are now in position to re-sag the center phase of the 34.5 kV circuit on top. After clipping to the conductor, the men attach a cable hoist and proceed to pull tension. Notice the barrier on the phase wire behind the men. The lower metal parts of the 55-foot hole and elbows are well protected from accidental contact with underbuild during work on distribution and sub-transmission circuits. While the men repairing this 22 kV switch would not be in immediate danger from such a contact, the truck body itself would become energized. To prevent this, the upper arm is protected by layers of black insulating tape, the lower arm by a fiberglass barrier. The 50 and 55-foot hole and elbows used in distribution and sub-transmission work have almost unlimited action. The lower arm rotates vertically through 120 degrees, the upper arm through 270 degrees. The base pedestal revolves continuously through 360 degrees. This high degree of maneuverability enables bare-hand crews in hole and elbows to reach positions inaccessible to many other types of equipment. The bare-hand crew is working 65 feet above street level on a 69 kV circuit. Since they went around, not through the underbuild, no cover-up was necessary. Work on the horizontal post insulators goes quickly and easily with ordinary hand tools. Warped or twisted poles in this type of construction pose no problem for bare-hand crews. For hot stick crews, well, ask them sometime. Using barriers on the double arm, the bare-hand crew is replacing a broken tie wire on the end of a 12.5 kV alley arm in another congested downtown area. The job quickly completed, the crew pulls away, carrying the largest cover-up material in the personnel buckets with them. Tools and smaller equipment are in the small tool trays attached to the far side of the buckets. Substation maintenance work offers many opportunities for the bare-hand method, since repairs must usually be made without interrupting service. In this 138 kV substation, work is speeded by the convenience of a Holland aerial elbow. In the brief period since the live line bare-hand method was first announced to the electric utility industry, it has won wide acceptance across the country. Because it saves time and reduces labor cost. Because it prolongs the productive working lifetime of valuable men. Because it offers greater safety, comfort, and efficiency. And because it solves difficult line and station maintenance problems without interruption of service. The live line bare-hand method is a major advance in the continuing effort of the electric utility industry to provide dependable, economical power to a growing America.